Swayam Prabha. Digital India. Educated India.
Always the conclusion of a talk or a statement was, okay, but these we have to guarantee, this assumption we have to guarantee through the connections. So now we have finally come up with understanding, or at least trying to give you some principles on how do we design the connections. You see, these statements are taken from the handbook on precast concrete buildings of the FIP, the International Federation of Concrete, which actually remarks exactly the concept that we have highlighted in the past days. So connections are an essential part of the prefabricated buildings. And as a matter of fact, well, what I'm going to present are examples, but they do not cover all the possible types of connections, because really the ingenuity of engineers and precasters has developed many, many solutions. But the important thing is that the overall behavior of a precast structure as you design it depends on the effectiveness of implementing the assumptions in the transfer of the forces between the elements through your connections. So which is the function, or which are the functions of connections in precast building structures? First of all, they connect the units to the bearing structure. The slabs among themselves, the slab to the beams to the columns, the slabs to the cores or to the shear walls, and so on. They secure and guarantee the intended behavior. So if we assume a diaphragm behavior of the floors, the connections have to guarantee it. If we assume a fixed edge at the bottom for the column, the connections have to guarantee it. And in order to do this, they have to transfer the forces from the point of application to the stabilizing structures. Then you also have other aspects. Function, so the connection must guarantee deformation, allow a deformation. Appearance. If you see a rusted connection, what are you feeling? That there is some kind of bad design, bad execution, whatever. Well, water tightness, sometimes through joints and so on, the water seeps through. Fire protection, fire resistance, durability. One thing that we have to take into account, and we will see some examples of very strange connections, is that, well, connections must be manufactured, must be then, in some way inserted or connected to the elements. And they, for this reason, must be simple. Also considering the tolerances. But so, as we said yesterday, when we talk about connections, it's not only the piece of steel which joins two elements together. It's the complex mechanism of transfer of the forces in the adjoining zones of the element that you have to consider. So a connection, broadly speaking, consists of three parts: the connecting device and the two end zones of the elements, if they are two, can be even more, that are connected. Well, the importance of the design of connections is evident in this building. Okay, this building was, well, not even a warehouse, was for a factory, a place where they hosted some machinery, some vehicles, and so on, forklifts, and so on. And 16 years ago, you see, in 2009, during the night, during the night, a very severe earthquake hit central Italy, the city of L'Aquila. Well, there were casualties because a building was a student house collapsed because of bad design assumptions, but that was not, we will not enter into that. So this was a warehouse, there was nobody in the night. But look at what happened. The building is there. The building is perfectly safe. Only what has happened? That this facade panel really collapsed outward. Well, what happens generally? This is a problem over which there has been quite some study after that. When we design a precast building like this for earthquake, so you see, what do we have here? We have the column here, and this is the main beam. So we design these frames as they are a system of frames. But here you have the cladding, which is connected to the system. And the cladding provides a large contribution of stiffness. Well, you see that also in this case, in this direction, where these cladding are, it worked pretty well because the walls are still there. But I think this was the main direction of the earthquake motion. But then what this resulted in? Resulted into a motion in this direction for which the connections of the panel were not designed for. So we are able to design connections between the facade, the claddings, and the structure parallel to the cladding. But for out-of-plane motion, that was much more difficult. So the structure stood perfectly. Well, luckily, there were no casualties because it happened during the night. This was an industrial building. There was nobody. But look what happened at the connections. These are some, let's say, rails. There is a sketch then in the forthcoming slides. This is a rail where a connection, which is really like a hook, connects the panel. This is the panel. This hook is mounted on the beams and is connected here. You see that it was really torn up by this out-of-plane movement. So these highlights really, and you see there was this is another part of that connection, which was really, went under tension and was broken because of the excessive demand. So this really highlights the importance of the connections. Actually, this building, where is that? This building stood. There was no issue to the behavior of the building. All was in the connection. Well, likely in this case, the damage was only economic because you had to replace the panels and so on. But can you imagine if that happened during the day and you had, well, this was like a warehouse, you had the forklifts bringing freight back and forth and so on, and you have people passing by. Could have been better. Some other images of the connections there. So generally these the panels, the adjacent panels are not connected. They are shaped with some kind of geometrical details. They are simply, joined to each other. There is no connection. Yeah, there is no connection. Because if you put connection, that is a good question. Thank you for asking. I said this gives you a very strong stiffness contribution. If you connect them, you have a stiffness contribution which is as large as the wall. Whereas if you do not connect them, you allow the single panels also to rock a little bit. So this, helps in controlling. Otherwise, that becomes a very stiff structure. The panel, the frame structure don't do anything, and all is taken by the panels. But those panels are not designed for other structural purpose than taking the wind load. That is all. No, thank you for asking. Good question. Thank you. What? Yeah, it was. Well, then this. That is non-structural. That is non-structural. Surely, non-structural element in that case you have completely distorted and you have to replace. But that was, I would say, the minor damage in that case. So we have three options to design the connections, including seismic actions. This is a general design philosophy. So we can, let's start from the top. Connections far from the critical zone, which was exactly what was done here. In a structure like this, what do you assume? Since you consider only the frame, the critical zone, what is that? The critical zone is the bottom cross-section of the columns, because you have a cantilever, and that is the only place where you can dissipate energy. So these connections here were far from the critical zone. So you slightly over-designed them. Why do you over-design? Well, you over-design because you want them to resist a little bit more. But in this case, what was wrong? Well, it was wrong the fact that the contribution to the stiffness of the building due to the external walls was not considered. You will see this afternoon, you will have a lecture on earthquake. If your building is stiffer, it means that has a lower return period. And this implies, with the criteria that we use for earthquake design, that you can have a higher inertia force equivalent to the earthquake. But that force, in that case, was not taken by the columns, was taken by the walls. Because the principle is that the elements participate in proportion to their stiffness. Those walls, as long as they are connected to the structure and form like a box, they are very stiff. They take the largest share. If you have connections close to critical zones, you want to over-design a little bit more, because in critical zones, you allow plastic deformation to occur. But there can be, we will see an example, there can be the case where you cannot, this over-design results so unpractical that your connection should be so complicated that you cannot comply with it. And so you have to go and say, okay, my critical zone becomes the connection. So I will dissipate energy in the connection. So in that case, you don't design the connection anymore for strength, but you design it for ductility. You have to check that your connection can guarantee a certain capacity, but deforming up to a prescribed level. So this is the philosophy. Well, now, this is, we have said, we have two philosophies of accomplishing this. Wet joints, emulative connections. Just, design, but then construct your building structure in such a way that you restore a cast-in-place situation, not considering ERE. Then you have dry connections. And, also for teaching purposes, what I've tried to do is that, okay, let's try to imagine a building, to figure out a building and see how many types of connections I do have, because each of them has to perform different functions. Well, I can have the roof element or the floor elements. And I have to connect mutually one to each other. First level of connections. Then I have to connect the floor or roof elements to the beams to the columns. If you have a multi-story building, it can happen that your column come in segments. If you have 20-meter high building, you don't cast a 20-meter high column. It will be unpractical, transport it, but also to lift it. So you cast in segments, and then you have to decide where to join them, and we have seen some examples. Joins between the column and the foundations. And these ones here, these are really the ones about which we know least. Fastenings of cladding panels to the bearing structures. Why we do know least? Because we make the assumptions that the bearing panels are non-structural. They are, while we design for earthquake, we consider part of their mass participating in the earthquake motion, but we don't consider them in the overall behavior. And this is a big mistake. This is a big mistake. But still, it's a topic of applied research. It's very important. So which is the function of these connections? Mutual joins between floor and roof elements. They secure the diaphragm action. Joints between floor and roof elements, they, when you have a diaphragm, you must guarantee, you must provide peripheral confinement. It's easy in cast-in-place structure because you put reinforcement and you cast a peripheral, beam. In precast structures, you do not have that. So everything is demanded to the connections. Joints between beam and columns, these are also most delicate. Because when we design our structure, we think of planar schemes. So we say, okay, what does a joint between a beam and the column has to do? It has to transmit vertical forces. Yeah, and vertical forces you transmit by contact. But when earthquake comes, lateral movement comes. So never rely upon contact and friction. Always provide a dowel. There has been, in the late 90s of last century in Turkey, Kocaeli, strong earthquake and precast structures where there was not the pin connection between the column and the beam. You really could see that the column were standing and the beam collapsed because it lost the support, because you have this motion. Well, you can have also, it's not like that, but you can have some, jumping of the beam on the column. But at a certain point, because of this movement, the beam really loses its support. There was no, cracking, yielding of steel, nothing. So the beam collapsed as a rigid body because it lost its support. Well, in different codes for different times in Italy, it's, I think, since the mid-70s, there is explicitly written, never rely upon friction connection. Because friction during earthquake can vanish. And you lose the support. Well, the joints between column segments have to guarantee that your column then is continuous from top to the bottom. The joints between columns and foundations have to guarantee that your bottom edge of the cross-section is restrained as appropriate. And these ensure the stability of the panel. But that is the conundrum that you have to solve. If you say, let's go back to this building. My panels, they do not participate in the earthquake response. What you have to allow is that your connection must allow a relative movement between the frames, which are quite flexible. These frames, you see how, slender they are. This is also the benefit of precast structure because they have a high return period and so a lower inertial force. But if the frame has to behave as such, it will have large deformation. So these connections here have to allow the panel to stand and the frame to move. So they have to allow strong relative movements, which is easy in this direction, but it's not so easy in this other direction, because in that case, they have to function first as a tie and then as a pushback. So that is also the technological challenge. About the joints between beam and columns, there is another thing. As I was saying, we consider planar schemes, but in the reality, a structure is a 3D assembly. So you have to support the beam in its own plane, but you have also to avoid that the beam tilts in the out of plane direction. So the hinge, if it is a hinge, must work in two directions. And it has also to provide some kind of torsional restraints, because this is something that you can expect. So these are some schemes of how the connections function. But now we will see some examples. For example, let's start from the top. Connections between mutual joints and roof elements. These slides come from a survey that we made in the, what was that, about 2010, something like that. We interviewed about 40 to 50 precasters in Italy and asked them, okay, for these 6 types of connections, give us a maximum number of examples of the most common devices that you have. we ended up with, hundreds of them. So there is not a specific, so this work was intended also to say, okay, there is a protocol for which you have to at least verify. No, the only thing is that you can design it. Then if you design simply by hand calculation, by finite element model, or by testing, there is no mandatory prescriptions, but we try to come up with a protocol, especially for seismic regions. We prescribe 3 cycles at increasing amplitude and so on. But you see, this was a company which produced this kind of element. If you have your specific element, for this kind of element, each company has its own signature one. You have to come up with a connection which actually can more or less work only for this. You see, what did they do? Well, they used 2 bolts. They used 2 bolts. Post-inserted, generally, you can leave a sleeve or a hole because it will be difficult when this is installed to go on the top of the building and drill the hole. So you must leave the sleeve, you must pre-insert the sleeve, and then you put the hole. And well, let's try to imagine, how do we design this connection? So let us imagine that we know the force. If I look from the top, I see an element here and another element here. I see this plate here, and I see 2 bolts here. So let us imagine that we know the force F, which is exchanged at the interface between the 2 elements. This force must pass from one element to the other. So which are the mechanisms through which this force is transferred? Huh? Yeah, what does it mean? Well, if the bolts are short, they work under pure shear. So the first mechanism is that you have to check the shear strength of the bolt cross section. And in this case, it's the area of the bolts times what we call FVD, shear strength. Well, since this is steel, the FVD is, for bolts, we use the ultimate strength divided by the square root of 3, because we use the von Mises criteria. In some codes, you find 0.6 FUD. 0.6 is 1 divided by the square root of 3. It's nothing like that. But this is, something, the new Euro codes has adopted this philosophy that they must have very simple formula. It's like if the 1 over the square root of 3 was difficult. I don't like this, because if I see 0.6, I start wondering where does this 60% comes from? Why 60%? If I see 1 over the square root of 3, I immediately know, since I'm talking about steel, that it's the von Mises criteria. So, a code, but, codes are written in most cases by academics. That is the conundrum. But Eurocode is a complicated process because there are about 30 countries who have to agree. And in this case, the British took the lead, and they wanted very simple formula and so on. But also in the codes, we must try to do our best to keep in a formula, the reference to the physics which is behind that. Otherwise, we lose the feeling of what we are doing. Okay, so that is the shear of the bolt cross section. And what other mechanism of failure can you foresee? Well, we do know that when we design a bolted joint, one mechanism of failure is the failure of the shear failure of the bolt. But then there is also the bearing failure of the steel element. So you will have, if I magnify this detail, you will have the hole, and you will have the bolt which pushes against it. And here the bearing capacity will be alpha times the yielding strength of the steel plate times its diameter times its thickness. Why alpha? Well, because you know the bolt pushes and you have a distribution of stresses which is like this. When you arrive here at the maximum, the other parts of this plastic area is still not fully developed. So you have to do some more work in order to fully plasticize. But these are, formula which comes from the design of steel bolted joints. And then there is another mechanism of transfer of the forces that you have to check here, which is for the plate, yes, but it's not that determinant. There is another one that we have to consider. Vertical, these are implanar forces. No, but for this force here, just for the force that I drew there. Well, you have, where should it come from, the tension? Yeah, but it's small. You know, what is this bolt acting against? It's concrete. It's concrete. So if you look at the bolt, if you look at this bolt here, well, on the other direction, but let's magnify. You have this one here. This is the stem of the bolt. But you will have that concrete is reacting. So if the bolt is short mean less than 5 times the diameter. This is the, discriminant length. You can assume that there is a uniform distribution of bearing stresses by the concrete. Well, equal to what? In this case, since we are dealing with very thin sections, I would say equal to FC. Because there, the concrete is actually subjected to triaxial stresses because you are pushing, but there is concrete around. But here, they are very thin sections. So I will not rely upon an additional contribution from the passive confinement. So in this case, it will be FCD times the diameter times this embedment length here. Actually, you don't find this in a standard. You don't find in a handbook or in a standard how to design this connection, simply because, as I said, we interviewed 40 precasters and we came out with 400 connection devices. So we said, well, there is no way we can standardize. We can provide principles. So these are, principles based on simple mechanics. You must make a model and understand how the forces go and develop your own method. Then what Professor was saying before? Well, this is a relatively simple connection, but if you come up with a very creative design of yours, then invest some money, go to a lab, do some tests, and through those tests, check not only the behavior of your connection, but that the design methodology and the resistance calculation formula that you have hypothesized based on the mechanics, that they are, fulfilled by the reality. We should try to come up, but the issue is always that the typology of steel joints is a little bit less restricted. So we can make a scheme and have some kind of generality. There also, if you go into, for example, Annex L of Eurocode 3, which is for, you have a lot of examples if the joints are not aligned to the stress and so on. I think that there could be probably some kind of effort in this sense. We try to do that, developing with the precast the Association of Precast Industry to develop a handbook for connections. But the issue was always that, okay, I am considering this connection and I'm missing that one. And in some cases, if the connection is too complicated, it has a patent, and so that is the difficulty. But it's generally an effort that should be done. Now, this is a similar connection. This is for double T elements, okay? Well, you see that what you do, you pre-insert, I try to draw this. You pre-insert in the slabs of your element some steel profiles like this on one side and on the other. Okay, something like this. Here, what you see, this one here, are actually, you see like this. But if you look from the top, you see something like this. And generally, in this case, there are two bars which are anchored into the slab in that way. Well, we have said we have to transmit a force, which is something like this. So why do we decided to put the bars in that way and not, for example, putting just one bar, which is simpler? Yeah, surely, because those forces can be alternate. Those forces can be alternate. And what is the way in which this connection work under alternate forces? Well, actually, this is a shear force for the connection, but then it becomes a tensile and a compression force in the inclined bar. And generally, we design assuming that there is no problem in the transfer of the connection force. The issue is the transfer of the tensile force. And how do you design it? Well, you design in the same way as you calculate a bond length or a development length for a steel bar. So you will have bond stresses FBD along the development length times pi phi, which is the area of the circle. And then you might say, okay, my development length must be long enough so that I guarantee the yielding of the bar, which is ductile, instead of the pulling out of the bar. Well, also this bar here is welded at this point. So you must then check that that welding resists a force at least equal to the yielding force of the bar. But that is the design of a welding. If you also look from the top, you will see that then these elements are connected with a plate, and you provide some welding here to connect them. You have to design that welding. Well, here also comes a criterion. You see, here we have the welding of the plates which connects the two devices, the two elements. We have the bearing failure, yielding or bond failure of the bars, and we have the failure of the welding of the single bar to the device. So how would you list, in order of a sequence, how would you like or think this mechanism of failure should occur? Which is the one that you want to occur first? And the one that you want to occur first is the breakage of the outer welding, because that one will allow you to have some slip, and only through that slip you activate the bond. Surely this welding here is the last one that you want to occur, because otherwise you break the bars and you detach there. So this also means that when you design a connection can have different modes of failure. You have to adopt what is called the capacity design. So you identify these mechanisms and list them in order of the way you want them to occur, the sequence you want them to occur. From generally, the least ductile one to you list them on. And for example, we can design the first welding for the force. We design the yielding of the bar, not for the force, but for the resistance of the welding on the top. And we design the welding of the bar to the C element for the yielding of the reinforcement. Another thing, why, or not why, well, we understood why we need to this diagonal reinforcement, but what will be if I had used, I drew it from the top. I had used a connection with a straight bar, not with the two inclined bars, but with a straight bar. Yeah, yeah, that is. So the issue is that here we also have a mechanism of interaction between the bar which pushes against concrete. But generally, this development length that we need is higher than 5 times the diameter of the bar. So in this case, there is a milestone paper by Elizabeth Vinceleu and Theodosios Tassios, did a lot of work. I think that Tassios now passed away because he should probably be around 100 years, but he was a fantastic guy, Greek professor, very tall man with a beard, very imposing. And he really is one of the fathers of the modern seismic design codes. They worked, especially this milestone paper is about dowel action in static and cyclic conditions. And they developed a very simple analogy. They said, okay, I have a force here, okay? So since this force is cyclic, so it can happen that it's also like this. You will have that your dowel pushes cyclically back and forth against concrete. The mechanism that they identified was like a pile in a cohesive soil. And if you draw out the and you say, okay, I have the concrete which is able to exert a reaction, but they identified that there is this length 5 times the diameter at which you form a plastic hinge in your dowel. So in that case, the capacity is not much related to the strength of the concrete because it's compressed. Well, you can crush it, but it's not like that. Rather than to the plastic hinge formation in the steel under cyclic conditions. Because we also know if you want to break a bar, what do you start doing? Start doing this. And after a certain number of cycles, you break it. And that is the same which happens here. So the weak point of a connection done in this way, but with straight bars which work like dowels, is that in that case, the capacity is still linked to some plastic mechanism because the formation of a plastic hinge is still okay. And we know we have formula for the moment capacity of a circular cross section is pi r to the 4th divided by 32 FYD. So we can easily calculate, but it's that under cyclic conditions, you can experience degradation. And your capacity in that paper by Elizabeth Vinceleu and Theodosios Tassios, they show that under cyclic condition, the capacity can decrease down to 50% what you measure in static. So you see the design methods that you can have, they are based on the principle of mechanics. You have to hypothesize the transfer of the forces and work out the mechanism like that. Well, about we said the capacity design rules. Well, if you go to a handbook of design of connections in steel structures, you find that you design bolted joints for the shear of the bolt, for the bearing capacity of the steel plate around. But you also prescribe minimum distances in the two directions. How are those minimum distances in the two directions calculated? Because you don't want the tearing of the net cross section and the the breakage, the torn off of the cross section. You want them to occur after the bearing capacity has been reached. So those distances that we respect automatically guarantee you that the net cross section will not be torn off. And they are calculated with the capacity design principle. So simply saying the resistance of the net cross section must be higher than the bearing capacity of the plate. So if anything happens, the lowest strength mechanism will occur. So this is just to tell you that, this is a field. I will not say interdisciplinary because it's mechanics, but it's a field where you have to bring expertise from different fields of structural mechanics and structural engineering, steel design, concrete design, fundamental mechanism. Dowel action is one of the fundamental mechanisms of interaction between steel and concrete. The other one is bond. So these are the mechanisms through which you design the connections. Well, here things start becoming a little bit more complicated, because you see we had inclined elements, different type of elements. The issue is also here, well, to take into account the tolerances. In this case, it's relatively easy because you will join some elements. Even if these C elements will not be aligned, you can still connect by the plate and it's okay. But in this case, what did they do? Well, they used this, you see this, C profiles here. They act like rails. This here, you have a C profile. You can imagine that it's like a rail embedded in the concrete. And this bolt here is not circular. It's really prismatic, so that when you tip at 90 degrees, you can insert in the rail, then you rotate and it's blocked. So this allows for, accomplishing with the tolerances if they are quite high. In this case, the tolerances were not because the production was superficial and so on, but because you had to join elements of different shapes in a situation of slope and so on. So this is an example of surely well, you use standard element because actually you use the same elements for connecting the panels to the structure. You use standard products, but the connection is a hardly standardizable device. Well, between roof elements and supporting beams, this is another very, very common device. You see, you have a double T element, and generally, what do? Well, your bolt, this could be pre or post inserted. You come up with this U profiling steel, which you can also precast inside the element. And you have a hole here. Through which, after that, you will have a bar passing. It's a bolt that you then tighten up. And on the flanges of this element here, you will have other holes through which you will bolt the connection to the concrete. In this case, generally, these bolts here, they can be post-inserted. You can even go and drill something Well, sometimes you say you can drill on the beam, you know where the position will be. So before, when the beam is on the ground in the construction site, you will go and drill the holes. You have your own, sizes and so on. But then be careful that the holes here on these elements must be not circular, but that be slots, because you always have to accommodate for some tolerances. This, I have to say, this was a connection detail which we found everywhere. So this is the most common one, the most adopted one, is the most simple, and I will say the most reliable. Then you can, figure out in different ways. In that case, it was a U profile. In this case, it's even easier. You just go with two steel angles, and you can easily post-install them, and it's very, very easy and very simple. Well, that is the issue. Actually, not. Well, you can have, zinc protection of the steel. You can have some anti-rust paintings and so on. But these are only these passive measures. Yeah. Well, this is absolutely similar. This is a slightly changed. In this case, you see, in this case here, in all the previous cases, we have the beam here, and the element stood on the top. Okay, this is quite common, but in some other cases, you can have an L beam, and the element sits, but you see that the top of the beam and the top of the roof are at the same level. Well, why this? Well, because you may have constraint on the total height of the building. The other thing, as we will see, imagine that you have a situation like this, okay? So this is the beam, this is the roof element, and below here there is the column. Let us see what does this imply in terms of structural design. Well, your column, as we have said, it's here. So you have your own scheme where this is the column, okay? This point here is this one, is the top of the column. But the axis of the beam is not at immediate contact with the top of the column. It's offset of half the depth of the beam. So actually, your beam starts here. So you have this zone here. You have this zone here, which you have to take into account, because that part there is non-zero. The beam, if you cover a 15-meter span, the beam can be 80 centimeter deep, 1 meter deep. So that is 40, 50 centimeters. So when you do your finite element model and so on, generally, these you provide with special elements which are called rigid links. And the same is here. You remember when we made the example, the centroid of this element is here. So with respect to the extrados of the beam, and most of all to the axis of the beam, there is a strong eccentricity. So you can imagine if an earthquake comes in this direction, the earthquake force is applied here. Before you transfer to the beam, you have to go through the, and there is also an effect of tilting of that element, which you have to consider. So the finite dimensions of precast elements, when it comes to structural analysis and also to the design of the connections, must be taken into account, because actually, if you have a force which is applied here, the effect will not only be this, which is easy. The effect will also be that you have a tensile force here and a compressive force here, which have to equilibrate that tilting moment that you have to take into account. And out of plane forces, yeah, out of plane forces as well. So this, to go back to the case that we were examining before, this case here is to limit, in a sense, this, piling up of eccentricities, because in this case you contain everything into this space. But the principle of designing this connection is exactly the same that we have seen before. It works exactly in the same way. Well, other variants. So you see, in this case, the beam was not an I beam and so on, was this inverted channel beam, and you sit the element here. So in this case, it was not anchored from the top. It was from the bottom. It was anchored from top. See here the slotted hole, which serves to accommodate the tolerances. Now here is another example of a connection which works only for this kind of elements here. This is an element with this wing shape here, but at its edges it has some like a stiffening beam, we could say that. This has a structural purpose because it serves to convey down the forces, but also as a functional purpose, because this element, generally, if you give it some slope, and generally you do that, you give it a slope to have the rainwater to drain. So then you collect here in a channel, you put some pipes, you give slope to that pipe, and you drain the water out. Otherwise, with these elements, the risk that you form ponds and patches of water and they stay there. And you have waterproofing, but waterproofing is UV ray sensitive. So after some while, there is some degradation and the water starts leaking through and you have durability issues. So how did they solve the problem of connections here? Well, you have this solid piece of concrete here, just drill a hole and have an anchor bolt go through there. This is another, rather creative, because you had this, skew symmetric, like a, seagull profile or whatever, and they connected. Still, you see, this is still a steel plate, steel angle, which was connected through bolts, through anchor bolts, to both concrete elements. Yeah, this requires a lot of precision, or as in this case, you see, you have slotted holes, you have 2 holes to accommodate, you have this rail to accommodate that. So this was the difficulty that we faced to end up with standardization, because this connection here, this one here, was easily standardizable. But then you say, okay, but we also realized that these connections were there, and so they required some specific issues. Other similar cases, similar element. You see, this is an image of the connections with the plates and so on. This is the upper plate, and you see these, dashed parts, which are the welding that you use to complete it. Other cases, this is a little bit more complicated, but it is based on the fact that you transfer through these platens, you transfer the forces to some hooks, to some bars, and so on. Connection between beam and column. This is the standard one, the most easy one. Well, you have your beam, which can come in different shapes. This is an I beam, this is an L beam, and so on. And you have this is the beam, this is the column. You have holes inserted in the beam. You have to preform them. And in your column, you can either have holes in which you insert then the bolt, or you can have the bars coming out. You have both options. Well, if you have holes where you insert in, you have to consider that you have then to complete with some filling, anti-shrinkage mortar, and so on. Yes. This one? No. This is the column, this is the beam, and these are the two elements coming. So there is no continuity, yeah. You can introduce a little continuity if you have some topping here and you provide some negative bending moment reinforcement. That will be very thin because the topping is maximum 5 centimeters. This is an example that we put here as some kind of bad connection. Don't do this, please, because you see, you have these very, very long bars which have to pass through all the depth of the beam cross section. But you see, the interesting thing, the reason we wanted to keep in this survey, the interesting thing is that you provide two. They provide restraints against the bending and the torsion in this direction. Well, these are some other elements, some other ways in which the same connection was realized, but generally the principle, you have a bar either coming up from the column or that you post-insert in pre-assembled holes. Always, well, I'm sorry that here the captions are in Italian, but here you always have a neoprene pad. And we realized through tests on full-scale precast buildings that in seismic regions, it has to be at least 1 centimeter thick, because the relative deformations which are required can really, compress the neoprene pad. So if it's thinner than 10 millimeters, 1 centimeter thick, if it's thinner, it can quickly squeeze and degrade. This is another typical connection which was used especially for the double thatched beams. The column is shaped in the form of an H. So it has two pockets on the top. And in those two pockets, you accommodate the beam. And you provide a bar which threads through. Well, let's try to see, for example, in this case, which are the mechanisms of force transfer. Well, surely you have transfer of forces here against the concrete here, and here, through the beam and through the column. And, well, they can be compressive, does not cause any problem, but they can be tensile as well. So the weak point, for example, will be the tensile resistance of a cross section like this. So you have to provide enough reinforcement there to resist this tensile force. If you have a out of plane moment, what this out of plane moment will induce? You see, look here. Actually, if you, I try, as I said, I was a very bad student in drawing, but if we try to see it in 3D, you see something like that. So actually, this part here, it will be like a thin cantilever subjected to a force. So you know the force because you know from your analysis, you know this distance, and the critical thing will be the resistant bending moment of this edge cross section. What about the bar which comes through? How would you design it? Well, you could say it's a bolt and you design like a bolt, but there is one assumption we must be very careful of. When we in steel design implement design of bolts, we make an assumption that the bolt is, we say, is a squat body. It's not slender because the bolt is a few centimeters long, some centimeters long, and its diameter is 10 millimeters, 16 millimeters, in some cases 20. But you know, you have this cylinder body whose length is similar to the diameter. And for this reason, we design it for shear only. In this case, see, the bar, the diameter will be 20 millimeters. But what it will be its length? Well, you can imagine that the beam there is minimum likely 20 centimeters. And then there are the two walls of this pocket. So you can have easily 30, 40 centimeters, even more. So that bolt actually is not a solid squat body, but it's a slender one. And is what? It's like a rope. It's like a rope. So you will have to design it for tensile force, because what this bolt will tend to do if there is a force, so this bolt will tend, a force which pushes in this direction, this bolt will tend to do this. So surely it will tend to deform. So it will be for its tensile capacity. But you also have to anchor. So this is the reason for which you have this. Never forget that you have to provide contrast plates. Otherwise, you can risk that for very heavy forces or very high deformation demands, like can occur in earthquake, you simply tear it off. And actually, this bolt here works or fails under a mechanism which forces the, it's something like this. You have a plastic hinge here, then you have a rigid here, then you have a plastic hinge here. So it will be like an articulated block chain. Actually, this mechanism of failure of bolted joints, they are typical of bolted joints in timber structures. Because while in steel structures, we have the bolt which connects the thin plates of steel elements, in timber structure, the width of a timber beam is 20, 30 centimeters. So this rope mechanism is exactly the same that we find in similar bolted joints in timber structures. So once more, you see how other parts of the discipline come into this. Joints between a column and the foundation. This is the typical one. Well, how do you design this element here? Well, we typically design with a strut and tie model. We have here the force which is transmitted by the column. And you have, what it happens is that you have struts going in this way, and you have a tie. Yeah, well, when the column is under tension, it can occur, but then you just rely on anchor, on development length. But the issue is that, okay, this guarantees the transfer from the bottom of your hole through the slab of the foundation element to the ground, because then here you are going to intercept the ground bearing, soil bearing pressure. But it can be this is, and at the cross section here you have also a shear force, but you have also a bending moment which results into forces like this. So this shear force here, which you see, it pushes against one of the walls of the hole. How do you design for it? Well, you design this wall as a slab with a concentrated force or a concentrated line force according to the model that you use. So you design it as a slab. And this slab is, you know, anchored, supported along these sides. So this means that the reaction forces here, let's draw them in blue, the reaction forces here, then go on the orthogonal slide, something like this. And you design this one here as a strut and tie mechanism, because you can say, okay, I might have a concentrated force here on the top, so I will have my tie here, and I will have my strut like this. So this will be the force in the tie, this will be the force in the strut. There are some prescriptions, but everything depends exactly on this design here, on the design of the lateral walls of the foundation wall. So you work out your model and your calculations as we have seen for the strut and tie, model. Yeah, foundation elements generally a strut and tie model. Huh? These ones here. Well, this can be functional. Well, here I draw it in this way, but you can also have that your strut goes down to here. This depends on how much width of soil you need, because if the soil is strong enough, you will need a lower one. Otherwise, you need. What is the drawback in this? Is that according to the principle of capacity design, you have to design the foundation for the maximum shear force and maximum bending moment capacity of the column. And since this element, you remember that classification, far from the critical zone, this is the critical zone. So the connection is the critical zone. So you have to apply here an amplification, an over-design factor up to 1.35. So you design for a force which is 35% higher than the strength of the column. Can be very high. Can be very high. And then in some cases in the code, it's also written that when you design foundations, forget all the ductility possibilities to reduce the forces. Because when we design a building for earthquake, we have some we call behavior factor, which account for the ductility of the structure and allow us to reduce the design forces. In the codes, somewhere, and now it's something that people start saying, well, but can become unpractical. It's written that when you design for the foundations, forget all those ductility coefficients. So design as if the building is perfectly rigid and linear elastic. So the forces on the foundation are huge, huge. I can show you, I will go a little bit farther, but I have some slides which can show you this kind of design, what it did result in. If we can magnify, probably here you see it better. You see, this was a precast building mock-up that we tested. You see the actuators. This column was 5 meters. This beam was 65 centimeters. The roof element was 50 centimeters. So here we are at 6 point something meters from the top. You see that these two workers, they have the, you see the foundation element here. You see how big is that? This is the ELSA lab. You could recognize the blue wall, yeah. Yeah. So you see the foundation element, how big was that? We had to transport 6 of them because we had 1, 2, 3, 4, 5, 6 columns. We needed 3 trucks because each truck could accommodate maximum 2. Well, this was for research purpose. We had the budget. Okay, don't care. But think if you have to transport in a real precast building, you have hundreds of columns, not 6. So you need the number of columns divided by 2 to transport that. So the design of this kind of foundation elements has become unpractical, and this is the reason for which, let's go back to screen. This is the reason for which another type of column to foundation connection has been designed, and it's now quite popular on the market. You see, you have this foundation slab. Generally, nowadays, the slabs are cast in place. You go there and you cast your foundation slab. And you put these bars waiting, and the column is equipped with this kind of, it's called column shoes, and it has this bar and this tail bar for the transfer of the forces. And so how does it work? Well, this is the foundation slab with the weighting reinforcement. Then you position your column, but here you still must hold it in place because it's still not connected, it's not safe. Then you pour anti-shrinkage mortar, and when it has set, you can release your column. TEIKO, yeah. These are, yeah, and well, there was, well, the one that I think we worked with in Italy, but was more than 15 years ago. I don't remember whether it was Alphen or something like that, but now they are called Liviat. Liviat has branches in the Middle East as well, I think, yeah. Also in India? Yeah, okay. Yeah. And this is the example, just to finish it up, this is the example, oh my God, of the connection of the facade element to the beam. You see, on the top of the beam, you have this rail here. And on the facade element, you have a similar rail, but while on the beam it's horizontal, on the facade you install it vertical. Then you have this element like this, and this particularly shaped hook, you insert here. Well, what you do is that since it's very thin, you insert it like this, then you tilt at 90 degrees, and you have it installed. And the same you do with this hammerhead bolt, that you insert like this, and then you tilt that. And then you tie up with this washer and nuts and so on. This guarantees you a little bit of flexibility, surely tolerances on the positioning, absolutely. The fact that there is this, thinner section here allows you for some deformation. But what happened during L'Aquila earthquake, that because of, actually in that case was the out of plane deformation. And you could see from the picture that this very thin profile were opened up, torn off, and this part here was broken. This is actually one of the most difficult connections to calculate, because also to understand the transfer of the forces. And this is one of the connections where you accept the design by testing. So you do the tests, and then you analyze the test results, make reliability analysis, and say this is the maximum force that they can withstand. Now let's see, we have still 15 minutes, I would say. Let's see, Let's see, now, yeah, we have time to complete slides, even if they are not, we have time also tomorrow, don't worry. Yeah, there are a lot of materials, yeah. But that is, you can also keep like a handbook and you go back. Let us see, we said, it's important that we guarantee diaphragm. Diaphragm is easy when we have a cast in place concrete slab. It may not be so easy when you have a discontinuous roof slab. But let's first of all try to understand how the diaphragm works. So let us imagine that we have a building, and the number of the naves in the direction orthogonal to a horizontal force is P. Okay? you have this horizontal force. Actually, the fields of your roof deck or of your floor deck, they behave like simply supported beam. Because the connections, they guarantee the transfer of the forces, but you will not rely too much upon the. So if you have an FH force, totally, you divide by the number of the base, and you see you have F half. Here you have F half plus F half, so this is and F half. So this model here is, if you want to see it in a simpler way, you have two beams like this, and P here is equal to 2, so you have FH divided by 2 and FH divided by 2. What do you have? You have FH by 4, FH by 4, and you have FH4, FH4 here. So this is very simple equilibrium model. What does diaphragm action require? It requires compatibility. So you don't want 1/4, 1/2, 1/4. You want 1/3, 1/3, 1/3. Because the assumption is what? The assumption is that behind this roof deck, there are some lateral load resisting elements. And because of the precast logic, you will make them all equal. It's true that also for axial forces, this column take less than this. But, it could be probably more cumbersome to have them of different sides, or difficult then also to accommodate, because if they have different sizes, then cross-section changes, connections, and so on, than having this. But anyway, the stiffness, if the stiffness of this frame is equal, you will not have 1/4, 1/2, 1/4, but you will have 1/3, 1/3. So this is what you want. So you have to guarantee, let me cancel this because otherwise we do not see it. You have to guarantee, you see, that part of the force which tends to go by equilibrium on the inner frames is redistributed to the outer ones. That is the principle explained in a very simple, force-wise fashion. So actually, you have to download the central one and to, overload the lateral one. What does this result into? You see that it results into in an in-plane bending action. Well, if you have a continuous cast-in-place concrete roof deck, this action is taken by membrane forces in the slab. But if you don't have it, and this is the case of two roof bays, how the force goes, if it's not, it has to be taken by the connections. That is exactly what does it happen. So this force Q here, this force Q here is, this force Q here is exactly this transfer of the forces from the central base to the outer ones. Now you can have different cases. In the best case, you have the roof elements, which, as you can see here, they are joined to each other, and you also connect them. So these forces are taken by the connections between the two roof elements, as we have seen before, were those connections with the V-shaped bars, for example. How do you calculate this force? Well, it's a very simple equilibrium model. You could say this is my diaphragm action force, which I apply because of stiffness in the middle of the roof element. So Q times this lever arm L half must be equilibrated by the forces along the connection. So you have the number of connections, And you can easily do that. And these forces have a lever arm, which is the width of the slab. So once more, it's a quite simple, I would say, mechanistic model. You also have these reaction forces, but you see, this is the effect that I was telling you before. The inertia force is applied at the level of the centroid. These reaction forces are at the bottom. So together with this, you also have, well, if the force is like this, will be tensile on this side and compressive on this side. You have to consider that as well. So this force S, which comes from diaphragm action, is the one for which you are going to design that connection that we have seen before. Well, a particular case is the edge element, because where inner element has these forces on both sides, the edge element has these forces only on one side. And who provides the remaining equilibrium contribution? Well, you need to have forces on the connections, not only in this direction, but only in the other one. You see, these you calculate the formula which are there, you can easily derive because you write the equilibrium of rigid bodies. But just to tell you that now, a connection here will be subjected to a force in this direction, to a force in this direction, and to a force vertical. So it will be a non-easy state of, well, non-easy. You have to consider this, multi-directional stress state. Now let's make it a little bit more complicated. What if your elements are not connected, but they are spaced? Who can guarantee the diaphragm action? Who can guarantee that some force from the middle bay will go out? Well, it will only be the connections at the bottom. So what you have to guarantee is an in-plane. You see, this is a scheme. You are looking at your deck from the top. So these are in-plane bending moments. How do you guarantee those in-planes bending moments? You guarantee them through these forces parallel to the stems of your pi element. What does this also imply? What does this also imply? That if you have a roof element which is made not with this kind of elements, but is made with elements like this, which will have only a point-wise connection, it will be very hard for you to guarantee diaphragm action. Because you see, here you are able to guarantee the diaphragm action because you have on the same element two stems, and so the forces can be on one direction in one stem and opposite direction in the other. You create the in-plane bending moment. How can you create in-plane bending moment only with one stem? And so typically, what it happens with, strongly disconnected elements is that you have, if you perform your modal analysis, you have a mode in which all the frames are in phase, but you have also a mode in which the frames are in phase opposition. And here really, here is a proposal of the simple calculation, but here you have to rely upon a modal analysis which you perform with a software. So these are very simple, ways to calculate the forces in the connection. Now, just to quickly go through, those were forces on the connections between the roof elements and between roof elements and beams. Now we go to the connections between the beams and the columns. And you see here Well, apparently, these are the same scheme. What is the difference? Those two schemes, are they different or are they same? Huh? Who thinks they are the same? Raise up your hands. So I assume that if I ask who thinks they are different, everybody will raise the hands. Where is the difference? Huh? Yeah, this is the extra D. This comes from the fact these two schemes, they represent the same structure, you know. But in one case, this is the column and this is the beam. So this is the direction. And so you can say, I have a force here, but because of the high rigidity, I can transfer it here. The other scheme represents the frame in the other direction. So if you have a force here, you have to consider that there is this distance d. And so the connection between the beam and the column in the out of plane direction must be designed also for a bending moment and not simply for a force. So this is what we have to be careful of. Well, this is the easiest way. If we have a multi-story building and we have a column which comes into pieces, well, we have to guarantee the continuity. So for earthquake loading, you expect something like this. So at different levels, you can calculate your force. But going back, I think it was your second day lecture. Where are these columns among these connections among multi-story columns made? Well, generally they are positioned, for example, at mid-depth here. And why at mid-depth? Yes, because for gravity loadings, the diagram of the bending moment, except on the uppermost column, but in the other columns, has a 0 point close to the mid-8 of the column. So you put the connection where for gravity loadings, which are the permanent ones, are the ones that the structure withstands 100% of its life, there is no moment. And then for earthquake, which is an accidental design situation, you will design the connection which adequate, you know, overstrength coefficient and so on, so that it withstands the required moment transfer capacity. We assume, yeah, we design the connection so that it guarantees the continuity. Because even when we put the connections there and we design for gravity loads, we put the connection where there is the 0 moment, but we don't say that there is a hinge. So the moment is 0 because it will be 0 assuming the continuity. So we have to guarantee the connection. Otherwise, your column will be a chain, will be not. And this is, you know, schemes of the design of the foundation elements. As you say, you see, we said we design for a bending moment and the shear force, which are not the ones coming from the analysis, but are related to the strength of the column. And we apply an overstrength coefficient. Yeah, we can do this, and then we will see the example in case tomorrow. So actually, how do we design a connection? Well, as we have seen also here, we have mainly focused, when I said the design, we have focused mostly on the design of the connector. But now we have to understand how the forces are transferred in the adjoining elements. So basically, we have compression, tensile, and shear forces. This is the way we transfer. Well, compression forces are transferred either by direct contacts, by mortar pads, or by other type of bearing elements. Avoid direct contacts. Avoid direct contacts. Well, mortar or microconcrete to level irregularities And these are the normal thicknesses of the joints that you can have. Soft bearing materials to accommodate irregularity, to smear out, to smooth the distribution of the stresses. Minimum thickness of soft bearing pads equal to 10 millimeters. Hard materials can be used. You can find some steel pads as well for specific requirements. Tensile forces. We have seen a variety of steel connectors. Anchorage by bond. That is the main thing. Since you want that connector to yield, you have to provide adequate bond length. That is essential. And well, you can use bolts, you can use welds, and so on. And transfer of forces, well, bond between steel and concrete, friction along interfaces. In some cases, you can have interlocking by shear keys. For example, in hollow core slabs, one common mechanism of transfer of shear forces was through shear keys like this. So you have in your elements some pockets like this, and you could have also some reinforcement coming out here, and you transfer the shear forces through a strut and tie mechanism. This is the strut. These are the ties. And you can reverse it because when it's cyclic, you reverse it. Allowing for the, contrast forces which could be developed. These are empty pockets. When you join elements, you have to complete with the cast in place. Some people, besides the bar, also use fibers because they allow it for better distribution of forces. Okay, I think that we ended up with the fundamentals today. Yeah. 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 Yeah, also you. Yeah. Or you can cover. Yes. Yeah. Yeah, that's true. In Italy, there was also another thing. Since we have to cover this joint, I have some examples there. I don't know whether tomorrow we will have time. There was the development. We put there some energy dissipating devices to help through the friction to do that. Okay, well, now